Last but not least, we have James, who's going to talk to us about how to use padding to defend against traffic analysis. There will be no technical issues. The slides will come right up. Turns out I'm great at manifesting. All right, take it away.
Thank you. So talking about adversarial padding-only traffic analysis defense. The other authors and I are from the University of Minnesota. Okay, so just in case you haven't heard enough about Tor, I'll go over just the important bits here. So it's a privacy and anonymity network. Importantly, so the traffic gets sent through sort of randomly chosen volunteer-run relays, 3 of them typically. The traffic is encrypted, and then at each sort of hop, parts of it are stripped away. And the important part is that really only each relay only knows where the traffic is coming from and where it's going. So really, no relay knows both who's sending the traffic and where it's going, at least not at the same time. Illustration here. So the relays are just chosen randomly from basically a large set of them. A lot of people use Tor. It's important. So any sort of possible angle someone could get against Tor users is fairly important. So there are a couple different traffic analysis attacks that are just sort of inherent to a lot of low latency and anonymity systems like Tor, but could hopefully be defended against. One of them is called website fingerprinting. So in a website fingerprinting attack, you have a passive adversary that can eavesdrop on traffic going into the Tor network. So like in my diagram, that'd be on the left side. This could be the first relay in the network. This could be an internet service provider. It could be a system administrator where the client is accessing Tor. Basically, since they know who's sending traffic to the Tor network, and then use traffic metadata. So that since the traffic is encrypted, they can use the packet timing or packet direction in the sequence. If they can use that information to guess the website someone's looking at, then they can sort of de-anonymize them and break sort of privacy guarantees. And these sorts of attacks can be effective, especially with deep learning. And if you think about it too, when you download it, or when you go to a certain website, there might be hundreds of packets exchanged with that website, and so you might actually have a fair bit of information that gets leaked in terms of what you're doing. In website fingers, or in machine learning and deep learning right now, it might seem that attacks only get better. People keep coming out with better and better sort of techniques, and a lot of times those have been getting applied to traffic analysis as well. So how do you defend against it? That's an area of research as well. Usually 2 of the major techniques would be to either add fake packets to sort of obfuscate the real traffic, or delaying traffic to also to sort of reshape it in a sense. In the kind of defense strategies as a whole, sometimes people might have a defense that tries to make all the traffic look like each other, so that it's hard to distinguish. It could be that this random padding is added to sort of obfuscate the underlying real traffic, or maybe the connection is actually split among different circuits, for example. So in this attack, maybe an adversary, let's say they watch traffic going into Tor, maybe from a crawler they're actually running themselves, try to sort of make a database of what the traffic to each different website looks like, and then given someone's actual traffic, they can then do maybe a sort of multi-class classification type problem where they actually predict the website that the traffic's associated with. Okay, and then there's one other sort of major attack that we'll be discussing. It's called flow correlation. So if you do manage to get a vantage point both going in and getting out of Tor, so maybe like an ISP or a malicious relay, then you can sort of try to correlate the flows. So if the flows look like they're actually part of the same sort of connection, and you're able to, then you'll be able to also de-anonymize the user. A lot of the early attacks, they use more statistical correlations. Maybe they would just have like a vector of the volumes of traffic at different points, and those worked okay, but those weren't really enough to overcome the sort of base rate problem of if you have n flows going in and n going out, there's n squared possible correlation. So you need a technique that really works well and has a low false positive rate. And also Tor does reshape the traffic as it goes through. So it's not really a trivial problem of just saying like 800 packets went in, 800 went out, because the actual shapes of the traffic on the incoming and the outgoing traffic are actually different. So the most recent state-of-the-art techniques like Deep Coffee do use deep learning and a lot of data and sort of learn how to characterize the shape of traffic on both sides of the network to tell if they're similar enough. Okay, so how do we defend against this? Since a lot of the most recent techniques are deep learning based, it might seem natural to use adversarial sort of machine learning techniques. Um, and there is some truth to this, but it's actually much more difficult to apply against Tor traffic than against, let's say, images. Maybe you've seen examples of someone just, oh, here's a picture of a dog, but I changed these 3 pixels. Now the classifier says it's actually a cat. You might want to do this to traffic, but it's actually difficult, and there's a few reasons why. One of them is that if you, let's say, make all the Twitter visits obfuscated to look like Google visits, and all the Google visits obfuscated to look like YouTube visits, then an attacker, once they see you publish your defense, will just say, well, we'll just use that defense, make a new data set, and retune our existing models to know that, when if it looks like YouTube, then it's actually, like Twitter, that sort of thing. So you can't just naively apply this. The other really hard part is that you have to do this in real time. A lot of times in the adversarial methods in like computer vision, you know what you are trying to obfuscate. So you know the underlying image. In this case, you have to start sending the obfuscation or the padding packets while the page is loading, but you don't know what the rest of the traffic is going to look like because it would be very hard to have, let's say, a database of what all the pages on the internet look like. So these are a couple of major challenges. And we also try to make a defense that's random, also just because if we added padding packets in a predictable way, then the attacker could simply sort of subtract out the fake packets and know what the real traffic look like. Okay, so what's the core of the approach? So we've kind of taken inspiration from GANs, or generative adversarial networks. So we have sort of 2 competing neural networks, and one of them aims to disguise the Tor traffic, one that tries to identify it. The generator takes in a vector of noise. That way, sort of each time it generates a very randomized sort of defense strategy, and that prevents sort of adversarial retraining in a sense, where it makes it harder for the attacker to simply generate a large data set of what the defense does and then attack it in that way. And kind of like in GANs, the generator is optimized to maximize the loss of the discriminator and vice versa. And one of the key points is to take into account that you have to apply this in real time. The generator part is actually like a long short-term memory network, which is a kind of recurrent neural network, so it makes decisions throughout the sort of download of the website, whereas the attacker just uses a discriminator. And again, to emphasize it, so in this case, we are assuming that whatever defense you put out, an attacker is going to try to simply retrain their model to best attack your defense. And so we're trying to create the best defense in this situation. And part of the reason we use an LSTM too is that while you can come up with decent defense strategies ahead of time, it is nice to be able to have your defense be able to sort of take into account the traffic it's seen so far, to let's say like 5 seconds into the download, to kind of tune the strategy going forward. And then there are a few more complications to this. It's difficult to sort of represent the data in a way that would be, useful in deep learning, and also be able to use, like backprop and represent the data in like more like differentiable manner. So, because adding a packet is sort of like a discrete operation. So to fix this, we actually represent the raw traffic data in bins. So we bin it by the amount of volume over a certain period of time. And that's used as input for both the generator, and then the discriminator takes as input sort of the defended traffic. In the website fingerprinting setting, we create an embedder, so that basically sort of uses triplet loss to kind of characterize traffic for different websites. And then, so instead of actually predicting the website itself, the discriminator is trying to create the right embedding that the embedder would have given as a proxy for how well the discriminator is able to characterize or identify the traffic. Though in the flow correlation setting, there are simply just 2 networks. The discriminator is trying to say, are these 2 flows correlated? The generator is trying to add traffic in a way to make it so the discriminator doesn't know if they're correlated. So then we're talking about the binning. So the generator creates, let's say, like a vector of how many packets to send at different points along the trace. So this is applied to the download traffic, and we found a lot of web browsing traffic because of just the whole kind of request and then reply sort of way that the web works. The amount of upload traffic usually in terms of volume closely mimics the download traffic, at least in sort of shape, except it's usually just some fraction of it. So we kind of say, okay, we're going to pad the upload traffic up to 1/5 the volume of the download traffic. And usually the upload traffic is actually less than 1/5 the download traffic, but if we pad it up to that number, then the ratio typically stays about 1/5, and that doesn't leak as much information. I'll go over this quickly. So like the core of this doesn't matter as much, but if you look at the bottom left, it shows the input at each time step is some random noise, the amount of like the volume of traffic in the previous time step. Well, really in this time step, but in the time, and then the output padding is applied to the next time step. So the LSTM is just trying to kind of continually take into account its past decisions and what the traffic looks like while determining the best amount of padding to add to the next step. And it does this across 256 bins. So then we evaluated. We used some past data sets like the deep fingerprinting and the big enough data sets. In flow correlation setting, we used the deep coffee data sets. And we tested defenses by just simulating this defense on these data sets and then using that whole data set as input for the attack. In the closed world, so it performs better in terms of decreasing attack performance, by using the TikTok and deep fingerprinting attacks on these data sets. And on the deep fingerprinting data set, it does somewhat better than any of the kind of sort of comparable padding only defenses. And then on the big enough data set, it outperforms even more. We think it is better on the big enough data set, mostly just because the big enough data set has the subpages for each website, so it's basically more web pages that it can confuse with one another, whereas the deep fingerprinting data set just uses the home page. In the flow correlation setting, it also outperforms sort of comparable padding only defenses. Now these defenses are often designed for the website fingerprinting setting, but we decided to, why not also try it again in flow correlation. For example, it brings the true positive rate for a false positive rate of 10 to the negative fourth down to about 1/2 of the front's true positive rate for the same false positive rate. So yeah, in conclusion, it's designed to basically be a website fingerprinting defense. It can be applied in real time and sort of uses ideas from adversarial methods and machine learning, and especially to resist the fact that the attacker is going to just tune their model to attack your defense specifically. The generator is applied on download traffic. It could be deployed. We deploy with a pluggable transport in Tor. It appears to outperform comparable padding only defenses. And in future work, we could also consider trying to support the use of traffic delays, which might be even more effective, or looking into other deep learning architectures. So that concludes my talk. Are there any questions?
Let's thank the speaker. Questions?
Nice talk, thanks. Sorry if I missed it, but what kind of overhead did DeTorrent tend to add in terms of bandwidth?
Oh, yes. So I think we try to make all the defenses we tested about the same. I think it was around 90%. We have it in the paper, but I think at least we try to keep it around 90%. 90%
meaning you add an additional 90%?
Yes, sorry.
Yeah. That's okay. Yeah.
Other questions?
And we chose 90% too, because I think some of the state machine-based defenses had that, and DeTorrent and some of the non-state machine defenses were easier to tune, so we just tuned it so they were all about the same. The defense does get more effective as you increase the padding and less if you decrease it, but of course there's a trade-off there.
Okay, I'll ask one. Some recent work has shown that the front part of a trace is more informative than the later part of the trace. Does your defense work indiscriminately across the trace, or does it do something different at the front versus later on?
Yeah, so a big part of the DeTorrent sort of output is how much do you apply kind of at the front or later on. It does appear to actually be a lot like the front defense, and it does actually take this into account. Where just printing out the defense strategies when I was doing the work on this, it appeared that it was adding most of the padding packets to the front. As well. So yeah, it appeared to have learned this itself. Though I will say that it did randomize this, where sometimes if there wasn't a lot of traffic at the front on the original traffic, it would add like a big front download. But if there already was a lot, it would just not add more. I guess to sort of trick the attacker into thinking maybe that could have been the fake traffic. Because a lot of times it seemed to operate in a manner that just makes it confusing for an attacker to know if certain packets are actually the real ones or the fake ones.
Okay, cool. And then do you have your tools available online?
Yes, they are on GitHub.
All right, cool. Let's thank the speaker again.